learn about new things. Now, we will take f equal to ma into normal and tangential coordinates. If you look at the name normal and tangential, meaning that the object was moving in a circular motion or curved linear motion. All right. So recall something that you learned in chapter 1 again, that when an object moves in a curvature movement, the center of the normal direction is towards the center of the curve, like you imagine you're drawing a circle. All right. So when you talk about particles or an object move in a curve motion, then in that particular time, you can draw three axes if you talk about three-dimensional movement. One is tangent. Tangent means the direction of the particles, but it's always at a tangent direction. Okay, and when you draw the tangent axis, the relationship between tangent and normal always 90 degree, and the direction, okay, and the direction of your normal is always pointing towards the center of your curve. Okay, try to recall back what you learned in your chapter 1. Okay, so when you talk about motion that move in the curve or curved linear motion, we will use tangent and normal axis. In this case, because this one is in three-dimensional, we have add one more axis, we call it B, or you can use it as Z if you want, but there is a vertical axis that represents the third dimension. Okay, and we put in the vector form here. The direction towards T, we use F UT. Again, we are using vector again. Magnitude, direction, magnitude, direction, magnitude, direction. So by applying what we learned in chapter 1, the last section about curved linear motion, F equal to ma, and referring to this diagram, you can write this formula by having Ft ut, which is this one is a combination of vector, magnitude, direction, plus n direction, force, magnitude and direction, plus magnitude and direction, force, and ub means direction of going up, equal to mat plus man. What about b? Why there's no b here? Why there's no b here? What do you think? If you see this equation, there's no b acceleration. What does it means about these particles? Let's open this question to the class. Okay, the question is simple. You look at this diagram. You look at this equation. You have F equal ma. You have F in all the components. You have T, N, and B. However, for the MA component, you only see tangent direction, normal direction, and there's no B component here. Why? Under what condition? The B is missing here or equals 0 here. What happened to these particles, or how this particle move? Let's ask the class, see if you're able to understand the question. Nageswaran, you want to try? When you look at this equation and this diagram, what do you think the MAB is missing in this equation? What do you think to these particles? How this particle move?
I think because the So we're looking at the tangential motion most likely. Then the B is not considered as going upwards.
Okay. So does this particle move along B axis?
No,
If you
sir.
don't have no, so yeah, good try, and I can consider it's a good answer. You imagine that your particles is moving on a paper, this A4 paper. So this A4 paper consists of T and N. This A4 paper consists of the T and N axis on this paper, and these particles are moving on this paper plane only. You assume that this is two is a plane, so your particles are moving along this plane only. It do not move outside this plane. So if this particle move outside this plane, then you have plus MAB over here. Okay, so this equation is just an illustration telling you that this particles is moving at the plane of T and N in a two-dimensional dimension. Okay, so we can write these three equations. If your particles are moving on the T and N plane and there's no movement um, there's no movement at the increasing B direction. So meaning the particles stay at the horizontal level of the motion. Okay, so all the force in B will be zero. This question or this equation is just tell you that you are having a two-dimensional scenario here. Okay, but of course, if you go out to work later on, you will have a motion for B. Okay, or even you after you get your first degree, bachelor degree, you want to do your master program by research, then most of the time you will deal with three-dimensional scenario. Okay, so again, this is the equation that we use when we talk about normal and tangential coordinates, or when we use these three equation over here is when our object is moving in the curve or moving in a curved linear motion. Okay, this one equals zero because it stay on the plane. Okay. All right, let's see the application of this equation. Okay, spend some times to read, or those you already download the tutorial question. Basically, you have the same question as what you see on the screen here. All right. Now this question, example number 4, is a race car scenario, where if you go to race car track for this category of tournament, the racetrack is slanted at a certain angle. Okay, slanted at a certain angle as the vehicle move along the path. So this question asks you to determine the banking angle of this one for the racetrack so that the wheel of the racing car will not have to depend upon friction to prevent any cars from sliding up or sliding down. So if you need to determine this angle so that the car will not slip up and do not slip down. Assume that the car ignore the size, ignore the mass. Okay, ignore mass, M, and travel in the curve radius R and V. Okay, now in this case, it tells you something. You ignore sizes, you ignore mass. So you just focus on the motion itself. So again, you solve this question using F equal to ma equation. You need two diagrams to help you, free body diagram and kinematic diagram. So you draw the free body diagram. So at first, I just draw the normal reference axis, and I draw my car as this one, all right? So then I add in my normal axis. Let's say this is my car. Huh? It's I draw because I cannot find a good picture. So I just use a rectangular to represent this car. Huh? Okay, to represent this car. So we just, in the exam, we just use a shape to represent the object. And as this car was moving, right, this car was moving, so we are talking about, we can see from the back of the car, you can see from the back of the car. So this is the normal axis where keep the car from sliding up or sliding down. This is a B. B means horizontal, movement of the car, the B just now, right? So the first thing we mark from the object here will be your weight due to the gravity acceleration. Weight equal to mg. So you draw the free body diagram. You put in the n-axis and the b-axis. And of course, this one is from the back of the car. Huh? You draw from the back of the car. Okay. Next. In the question, it say there's no friction force. So you don't need to consider friction force. So if there's a friction force, then you need to find the normal force that you've seen in example 1 and example 2. In this case, the question asks you to ignore friction. There's no friction over here. So you don't need to consider friction force. All right. So anyway, we just put in there just to quantify the forces there. Although the question say is the wheel. The wheel is, we need to find the angle so that there is no friction force on acting on the wheel. So in this case, we just find the friction force for the car first. So you have the NC. Again, NC is a normal forces that help you to find the friction force, right? And acceleration to the end to inside. Okay, let's say this is a curve. So there is a normal acceleration to the center of the circuit so that the car do not go up and do not go down. Okay, so there's an acceleration here. Okay, actually I'm combining in this case, in example 4, because I take it to a more advanced stage, or you can say your lecturer is lazy to draw another diagram. So I just put a acceleration diagram over here. So this is a combination of a free body diagram and kinematic diagram. So kinematic, you will see acceleration. So I just put acceleration inside my free body diagram so that I don't need to draw the same diagram again and again. Okay, so I remove the question and I focus on determine the banking angle of the racetrack. So equation of motion, I use all the direction to the n direction is positive. So F equal to ma. So in this case, all the direction to the normal direction is positive. So I derive this equation. Because of the weight pointing down, there will be a force that react to this weight on the track itself, which is a normal force on the racetrack. Okay. So I will just straight away I jump from F equal to ma equation to this equation. Okay. So what about the force in normal? So you just split this NC into horizontal axis and vertical axis. Okay, so if you look at normal, is the direction. So you use NC cos theta. Okay. NC sine theta equal to your force in n direction, because your W is not in n direction, W is in B direction. So you don't need to consider W in n direction. M, carry forward. What is the acceleration when you have a curvature motion? You still remember when you want to calculate your acceleration in a curvature acceleration, you use V square divided by radius of the circuit, or radius of the circle. Okay, this is what you need to recall from chapter 1, the one that we talk about object moving in a circular motion. All right, so acceleration in the normal direction, you use this equation, V square over radius. Rho is the radius of the circle. Okay. Any questions so far from here to here?
No, sir.
Good, eh? Okay. Again, this equation is from chapter 1, when you learn about curvature motion, a collinear motion. When you want to find the normal acceleration, you use this equation here. So you have two axes. Next one, you find about B. B going up is positive. F equal to ma, but in the B direction. You know that this car do not move up and down, right? This car stay at that particular racetrack. It do not slide up and not slide down. So you know that in this F equal to Fma equals 0, because the object stay in that position. Okay, stay in that position. It do not slide up, it do not slide down. So your MAB is 0. So you do the force part. There is a two force here. Your weight and your normal forces acting on the wheel or acting on the body itself. So again, you can split this one going up, and there's a force over here. So the one that in the vertical axis is this one. So you get NC cos theta, weight pointing down because our general direction going up is positive. That's why we have a negative mg equal 0. Now in test or in exam, this will be the careless mistakes, or student will stop at here. They will do not know how to proceed from here because they will forget. The question actually hints you that the object doesn't move up or down. So for B axis, MAB equal 0 when your object stay in that position. Take note on that. This is one of the careless mistakes in exam, or you will stop here. You will have question mark here. You don't know how to proceed. Okay, this one you extract from the hidden message in the question. Because the question will tell you the vehicle do not slide up, do not slide down, means it stay at B. Or you can say it stay at this center between the B and N axis. It do not change in B direction. Okay, so you have two equations here. NC M, you know. V, V, do you know? V, you need to check later. Do we have N? Do we have V? We have V. Okay, we don't have V. So you just eliminating these two by solving these two problems, meaning you going to rewrite this equation, rearrange this equation so that you can same pattern as equation 1. Equation 2, you rewrite, you move your mg to the right hand side. You get this equation. Sorry, too fast. Okay, you move your equation 2 mg minus mg to the right hand side. You'll get NC cos theta equal to mg. Why we want to move to the right hand side? So that we can directly minus, or we can directly use the elimination method. You can either use positive, you can use addition, you can use addition, you can use subtraction, you can use division, and so on. In this case, because we deal with angle, sine and cos, when you see sine and cos in your equation, think of tangent. Okay, think of tangent. You take sine divided by cos, you get tangent, right? Sine divided by cos equal to tangent. So basically, you take this equation divided by this equation, you cancel NC, you cancel the M when you divide. So this one divide by this one, you get this equation, V squared over GP. You get one trigonometry equation, tangent theta equal to this one. Again, this is from here to here is, you need to do more exercise, then you will know. Every time you see sine and cos, you automatically do division. Take this one divided by this one, you get cos. You get tangent. Okay? Or in your personal revision notes there, you write when you see sine and cos, straight away you use trigonometry equation. So you take the first one divided by second one to get trigonometry equation. Sine divided by cos, you get tangent. So you can take 1 divided by 3, you get this equation. The question asks you about tangent, the theta, right? I'll ask you about the angle of the track. So you just rearrange this equation, become inverse or arctan of V squared divided by G rho, or the radius of the circuit. Okay, so this example 4 basically is an exercise to develop or derive equation from the question itself. Then how we move from here in the test or final exam, we will start giving you some value. For example, after the first section A, derive the equation for theta. Section B, we will start give you some input. So what happened if the velocity so and so, gravity you know 9.81, and the radius of the track is given. What is the angle of the racetrack that the designer should, or the host of the tournament must make sure the angle is there. So this one can extend to application question. Okay, this is a derivation question, but it can extend to application where in the section B, after you solve for this equation, B, it will give you some value for velocity and the radius of the track. You can find the angle of the racetrack. Okay. Any question for example 4? Any question? Clear?
Yeah, clear, sir.
Good. All right. Next, look at example 5. Okay, let's look at example 5. Spend some time to read the question. Those with tutorial question, print out already or downloaded the handout, so you can read for question. I forget which question already, but it's inside the handout. So here in my slide is example 5. Is in tutorial, you go and find this diagram. It's just above this diagram. Yeah. Okay. Now this is engineering dynamic question, and it's application question. So what does this question about is that you're given a scenario when you have a platform that is rotating in this blue arrow. Okay, this big platform here is rotating in the, you can say as anti-clockwise direction. And then you have object or this that you tie to a center of the disc with a cable or with a rope. And then you pick this disc in the air while the platform is spinning. You drop from the rest, from the v equals 0, the d, the initial velocity is 0. Then you drop from the air. This will going to spin with the platform, right? So when this spin with the platform, the question asks you about the tension of the cable, right? So if you read through blah blah blah, basically it asks you, after you release, determine the time it takes for the disc to reach the speed great enough to break the cord over here. Means you will spin at a certain speed, then this rope here, this cord here going to break. And it gives you the rope maximum tension that to break this rope here is 100 Newton. The coefficient of friction is given, coefficient between the plate here and the platform is 0.1. So basically you're looking at, you're focusing on object D here. Okay, it might sound a bit complex here, but you don't scare yourself. You just look at a normal object. Recall the standard procedure when you solve chapter 2 question. Remember, you always need 2 diagrams. And only remember, you only need solve one equation only. F equal to ma. Remember, 2 diagram, solve F equal to ma. Then you look at the question, slowly develop the free body diagram and kinematic diagram. Find where is the missing parameter from the equation itself. Then you slowly solve. Okay, so basically build diagram, solve F equal to ma. So always first you draw free body diagram. So I draw object D because it's the one that the question interested to know the time it will break, and this is our focus here, which is D. So when I draw D, I will draw my axis in this case because okay, how do you identify question in the exam or test? You look at the motion of the object. If the motion move in curvature or move in the circle, it fall under normal and tangent category. Straight away, you jump to the normal and tangent equation. If the object you see in the question is a straight line, then you use a normal F equal to ma and solve a linear motion equation. Okay, using the 3 Newton motion equation. Okay, so for this case, we are having a circular motion. So we are still looking at the normal and tangent behavior. So in this case, we have B and the N. B and N, I try to draw in the 3-dimensional so you will see what actually happened. So B and N. And then there's a T tangent normal there, tangent motion there. So T is the direction of the this D here, this object here. So we know that this object, when we drop this object, right? So as this object landed on the platform, it's going to rotate in this direction, right? So the direction of the tangent is this way, right? So that's why I draw my T is in that direction. Okay, again, when I re-engineer this question and put in the test or final exam, when I reverse the direction, don't use this axis. The axis will be wrong and you'll flip around. So try to understand the logic why I put it a certain way. It's not fixed. You have to depends on the situation. So draw the object, build the axis, because this one B vertical axis B pass through the center of the object. Normal always pointing to the center of the curve or center of the circle. We know that the center is this direction, right? This direction. And the only confusing direction is the tangent direction. It depends on the object, where does it move. Huh? So in this case, it's moved in this direction, right? Anti-clockwise, but if you release, you're going to follow this direction. So tangent is this direction. Tangent this direction, yeah? First thing I put in my free body diagram, always the gravitational acceleration factor will give me the weight of the object pass through the center, the CP or CG point of my object. Center of gravity point at the center, go down, W equal to mg. And just a hint, every time if the question gives you the friction force, after you build the gravitation, the weight or mg arrow, quickly go and put in the normal forces to calculate this one. Huh? In this case, I put nd to represent the object d. Okay, or you can just put an n there to represent a normal force to use to calculate friction force. Okay, there's a reason why we consider normal force in this case, because the question already gives you the friction force. So expect you need to use this one to calculate the friction force. Okay, we come to another confusion point or another area where the student will get confused. All right. Now we're going to explain the friction force. You know that friction always opposite your motion, right? So in this diagram, you are focusing on object D. The friction force is going this direction. I put in first. Friction force is going this direction for D. Why this direction? It will take you some time to imagine the situation, but to cut short, you just remember the friction force is, in this case, the friction force direction is the one that make this disc continue to rotate. Okay, just remember the friction force, the direction of the friction force is the direction that make this disc to continue to rotate and contribute to the tension of this cable. Okay, you just remember that you just assume this one as you rotating, you tie a stone to a string and you rotate your string, your stone, a slingshot like that. So you imagine the stone is going according to the rotation of your platform. You draw this arrow, and not another way around. Okay, so for this kind of question, you just assume, you just look at the motion, the friction motion that is the one that contribute to the motion of object D. Okay, in this direction. Yeah. So the friction equation is mu k, friction coefficient, times the normal forces n. In this case, I put the n sub d because this is object D. But in exam, you will put just a capital N. I will still give you correct answer.
Hello, sir.
Yes, go ahead.
Does the disc move in the direction of the platform or is moving?
Okay. Now, you imagine as yeah, it will be quite confusing when I ready this question, because this is the motion that relate to two body. It is not the conventional way when we look at friction, right? If you have a car that move towards to the left, the friction will move to the right, moves to the back, right? But this one is the relative motion that compare two body, D and the this here. Okay, but anyway, it will take some time to digest the direction, but I put some notes here. Okay, put some notes here. You just need to focus the statement where how you find the direction of the friction when you have two body interacting each other, because initially this body on the top do not move and the bottom is moving. So you actually are focusing on this object that doesn't move, and this object on the top is moving is because it's following the bottom platform. So this direction actually is following the direction of the platform. Okay. So you just read a few times, and then you drink a coffee, drink a tea to digest this statement. But for me, I will just give you some shortcut. You just assume when you have two body that relate to each other, when you let go and one stick to one another and rotate, you just assume by looking at the object that you focus on, and the friction direction is following the mother or the object that make it spin. Okay. So basically, this is a statement that support the argument of this direction. We are using the direction opposite relative motion to the track. Okay. All right. So just in short, you just imagine, because later you're going to use the force and the normal force to find the tension of the cable. So basically, the tangent component and the normal component that contribute to the breakdown of the line over here. Okay, so this one will take some time to digest, but you just spend some time to think about the relative motion between the two Ds lah. Okay. Yeah. Okay. Okay, so this is another add-on explanation why it's important to consider the arrow is following the rotating platform. Okay, because this force is going to contribute to the tension cable over here, right? Okay, and this component here, F here, is actually causing the D object or D this here to spin faster and faster. Okay, this force here, this friction force here is actually because of the normal forces here, is actually causing this to spin faster and faster. Okay. All right. Let's continue. The rest is just use F equal to ma to solve. Okay. This is the most challenging part. When I ready the question, this is the challenging part that took me some time to think how to explain to you guys. Especially you come to the friction force of this one. This is not a normal one body kind of scenario. If the car is moving to front, then the friction is moving to the back. But this one is because of two body. So the direction actually, when it flip back, is actually follow the mother or follow the platform direction. Okay. All right. Okay, now we need to focus after we have this one. So we have a tension over this direction at the normal direction. So we have a tension cable here. T here, we need to solve this component that focusing on that going towards the center of the plate here, which is in the normal direction. Okay, again, I'm lazy to draw another table or another diagram. So when it comes to kinematics, kinematics is MA. So basically I just put in the acceleration component there. So you know that when you have a normal and tangent component cases, especially for object for move in the curve, you have a normal and tangent acceleration. So I just put normal acceleration and tangent acceleration in the diagram. So acceleration of normal acceleration in n direction, and t acceleration in that direction. So basically this one, I combining two diagram. There's a free body diagram and kinematic diagram inside here. Right? Every time you talk about kinematics, you talk about MA, there's acceleration inside there. The rest is just mathematics. So you start with equation of motion. You look at the normal direction first, or you can look at tangent direction also can. But basically you talk about two axes n and t. So we start with n, F equal to ma in normal direction. You look at the diagram. On the left hand side, you look for all the forces. On the right hand side, you look for acceleration or motion behavior. Okay, so you can solve n and t, whichever you can start first also not issue. This one, you know lah, the disc doesn't move up and down. So you know that the first, the elevation axis B here is 0. Okay, FB equal to MAB equals 0 because the disc doesn't move up and down. It just stay on the surface of the platform. So FB equal to MAB equals 0. All right. Now, just some notes in your revision notes there. It's always, if you're given a 3-dimensional cases like this, always consider 3-dimensional, normal, tangent, and a B. Most of the case, student will forget about this one. You will do this one, but suddenly there's one unknown you're not able to solve because you miss out one dimension. There's one dimension that also do not tell you in the question, but is hidden within the diagram or hidden between the statement, because this doesn't move up and down. So there's one more dimension that you can use, which is the B dimension or the elevation direction, FB equal to MB equals 0. The next will be just looking at the diagram and put in the value accordingly. So for tangent, for normal direction, you only have T. You only have T because this one is tangent. So we look at normal, you have T. M is 3. Right, the mass of this here is 3 kilo. Right, this mass is 3 kilo. So M equal 3. And again, how you find the normal acceleration? You need to recall back. Normal acceleration is very popular. You need to use V square over R or over rho. V square over the radius of the circle. Okay, it's standard already. When you see a motion, object move in a curvature or circle, your acceleration for the normal always use this equation. An equal to V square divided by rho. This one also will not be given in the exam. You need to know by heart. An equal to V square divided by rho. Rho is the radius from the center. So you substitute. You know that the rho in this case is 1. Because in this diagram, I'm not sure whether you notice or not, there is a radius given in the diagram, which is 1 meter. So V square over rho. So basically, if you rearrange this equation, T equal to 3V square. There's one equation come up from the first section here. So this will be the first equation. And why we can put in 100 there? Because that is the breaking point of your cable here. So in the question, it gives you some value you can substitute. In this case, is 100 because the maximum tension of the cord is 100. So t 100 and 100 equal to 3v squared. So basically from here you know the velocity already. Okay, you can solve for v already, right? Next you look at tangent. Tangent you have friction in that direction, mu k and d. So mu 0.1 nd equal to mat. So m is 3. Acceleration at a tangent, you continue to write. There's two unknown here. Never mind. Try to solve using the fb equal to mab equation. Again, in exam or test, normally this one will left out by student because they forget there's one more dimension on a b. This one usually will help you to solve another unknown. Yeah. fb, f equal to ma in b dimension equals 0. So you put in the equation. So in the b you have w and nd. So nd going up, positive. Weight going down, minus 3, 9.81 equals 0. From the third equation, you can find what is your nd. Once you find your nd, substitute back here, you find your at. Here you can find already. So basically, you find your nd, you find your at, you find your v. So your at, just a cross check. Your at equal to 0.981 meter over second square. V equal to 5.77 meter over meter square, meter over meter, meter per second. And the resultant, okay, I call you can use the equation over here to find the time to break, right? He asks you to find the time it takes the disc to reach the maximum speed or to make the speed great enough to break the cord. So use this again, the Newton motion equation, V equal to V naught plus AT T. So you have the velocity, this one. You have the initial velocity where you drop from the air, start from 0. Acceleration you already find. Basically, there's only one unknown in this equation. You solve for the t, you get the answer already. Substitute the answer. Velocity 0, acceleration this one. Solve for t, you get t equal to 5.89 seconds. So this scenario, if you run in the experiment, we are expecting through this experiment, we were expecting the cord here or the line here will break after around 6 seconds. Okay, this is 5.89. Okay, so in experiment, we expect it will break around 6 seconds. Okay, sometimes it will be faster, but this is an analytical calculation. Yeah. Any question? Any question for example 5? Everyone good? Everyone good?
Yes.
Okay. Good, huh? Okay, I think we stop here and then we continue example 6 in the next lecture. Is that okay?
Yes, sir.
Let me stop the recording.